All right, chemical reactions, chapter 11. Skipping over chapter 10 for a minute because this is information you're going to need for your your own chemical reactions PowerPoint tomorrow. I'll give you the full instructions and rubric tomorrow. Tuesday and Wednesday you'll be downstairs in 127 making a 12-slide presentation with 2 of each type of the chemical reactions we'll be talking about shortly. So you'll get that information, and I'll have Mr. Wilson you guys will report just straight to 127. Those of you who are testing need to make up the midterm exam. Make that up first and then start on it. Start on the PowerPoint. You can make that up as needed. All right, chemical reactions, there are some basic information that we need first. And first let's talk about some arrows. Now, reactants are always on the left-hand side of the equation. It's what you put into the chemical reaction. You get products out on the other side, and we use 2 types of arrows to tell us something about that reaction. And if we use a forward arrow that has no indication of going backwards, this is an irreversible reaction. So if you see that one type, it's irreversible. If you see this stacked kind of back and forth set of arrows, this is a reversible reaction. Once this system hits an equilibrium, it can go back and forth depending on what pressures you put on that chemical system. All right. Then we have systems where we have to put heat into the reaction, and if a system requires heat, we call that endothermic. Endo for into, and then thermic again for heat, so into heat. And if you notice, this is very much a forward reaction. Next week we'll be making magnesium oxide with a lot of heat, and once you get your MgO here, it's very, very difficult to, you can take it apart, but usually requires electricity or something else. Then there are the exothermic reactions. Heat is coming out of. So those are reactions that usually require a little bit of stimulus, heat to get going, a spark, as in the case of gunpowder, or some other kind of initiation. And then once they get started, once you light a Bunsen burner in there, it is putting off lots and lots and lots of heat. All right, so irreversible reactions, reversible reactions, endothermic reactions, and exothermic reactions. Matthew, I've been in front of you the whole time. Guys have any appropriate check marks and such? All right.
What page is this?
This is 52 on your index. Now on the back side of the index. Matthew, I'm going to talk from this side this time. Only downside of this setup here. All right, these are symbols that you need to know and understand. Just making sure I'm in frame over there. The yields, so the arrow, when I see the arrow and I'm reading the reaction, I say yields such and such. Magnesium plus oxygen yields magnesium oxide. Just a little review, this is a reversible situation. The arrows can be, of either style. Now, the 4 types of states that you are going to find your reactants or products in. If you see beside, let's say, here's sodium. That's not a great marker. Here's sodium in the equation in an aqueous solution. That means I've dissolved some sort of sodium salt into water, and so I have reactant or product is in an aqueous system. The italicized L means you're working with a liquid, S solid, and G gaseous. And so those are critical to understand, especially we'll be doing a couple of precipitation reactions, and we start with some aqueous solutions and we get solids out of them. All right, these symbols, if on the top of the arrow you see like this delta sign, or heat, means that we are heating the reactants. If we are putting pressure on a system, you might see the word pressure, or maybe you actually see the pressure written up there. For instance, 760 millimeters Hg, which is atmospheric pressure, so you wouldn't do that, but let's say it was 1760 millimeters Hg. That would certainly be over normal atmospheric pressure. Likewise here, the temperature, if the temperature is not ambient or room temperature. And then finally, this catalyst here, and manganese oxide, not magnesium, but manganese oxide. If you needed something to make that reaction go, that's where you'll see the catalyst listed at. So again, all critical things that you need to read when you are reading equations tomorrow. All right, catalyst. This is something that you put in a chemical reaction to make, we call it lowering the energy curve. Here we have an endothermic reaction. This is an endo. And everyone should be on this slide at this point, making some notes. We have an endothermic reaction. This needs a lot of energy to get going. As in when we make magnesium plus oxygen yields magnesium oxide, and that's not a balanced equation, but that will do for right now. To get these two things together, we need a lot of heat, Your crucible next week will be glowing cherry red. And please don't pick it up without tongs at any point, unless it's like 20, 30 minutes later. All right, so we have the endothermic reaction, and what the catalyst does is lower the amount of energy that's needed for that reaction to take place. All right, so the blue curve is the activation energy. Underline that, that's got to be a term you need to be very fluent with, activation energy. And then this top one, which needs so much energy, is without a catalyst. And the lower one allows the reaction to take place if you have a catalyst. And the definition of a catalyst, it increases the rate of a chemical reaction without itself undergoing any permanent chemical change. It's just there. It helps, it's kind of like maybe a travel agent. It puts you and your trip together, but the travel agent is still there next week to help somebody else. Catalytic converter, we all have those in today's automobiles. We're trying to get rid of nitrous oxide out of the air, and so we've got nitrous oxide coming in with the dirty exhaust, and your catalytic converter will take that out. Now, has anyone ever parked a running car over grass, over dry grass for a little while? If it were very, very dry gas, you could light a field on fire. Because this catalytic converter, while it still has done this, lower the activation energy, it still gets really, really hot. Don't go under there, as soon as you've stopped your car after running it for a while and put your hand on it, you will get burnt. All right, anybody know what temperature your brain cooks at? 400 million degrees would certainly, kind of vaporize it. All right, your brain, and this is critical, guys. This could save a life. Your brain cooks at 106 degrees Fahrenheit. Fahrenheit. We'll see everyone write that in. Write that in. Your brain cooks at 100 degrees Fahrenheit because it's proteins. Proteins will start to, the word is denature at this temperature. And this is why it's so critical. All right, so normal body temperature is 98.6 degrees. No one, I was going to say, sweats a fever of 101, but yeah, eventually you might. That's not a big deal. We all spike 101 fevers. At 103, we really need to get that fever down. And if you are spiking, have a severe infection, fever of 105, that's about time to get you in a cold shower, cold bath, or at the hospital under a cooling blanket, or even in a water bath. You've got to keep your brain from hitting this temperature because you will start cooking. You'll start cooking. And I've seen it happen.